Greetings and welcome to the video introduction to the Chemistry 222 Exam 1 review, and I'm really glad to have you here. In the normal Chemistry 222 lectures, I would present some questions. I would then wait for students to answer the questions on their own, and then we talk about the actual answer to the problem. So it's a great way to kind of test yourself. And in this video, I aim to do kind of the same thing. I'll present some questions. I'll then ask you to pause the video, so pause it on the device you're using. You can then work on the question, and then when you're ready, you can unpause the video and I'll talk about the answer. So hopefully this will be a great way to help you prepare for the midterm. Now, this page you must check with me to make sure that all the information is correct. But what I plan to have happen at the time that I'm making this video is that your midterm will be over chapters 7, 8, and 9. So chapter 7 was stoichiometry, limiting reactants, jazz like that. Chapter 8 was the gas laws, and chapter 9 is the energy chapter, where we talk about calorimetry, delta H, Q equals MC delta T, stuff like that. So when you come to the midterm, make sure you bring your calculator, something to write with, i.e. a pencil will be cool. Bring the completed calorimetry lab. You'll bring the exam prep worksheet 1 with you, and exam prep worksheets, which will be due at the time of your midterm. It's a series of questions where the answer is given at the bottom, and your goal is to show your work how you go from the question to the answer in detailed steps. So anyway, check that out. You'll also want to bring a printed copy of the chromatography lab. We will have a lab after the midterm. It'll be the chromatography lab. You'll be ready to go, and bring your safety goggles. The midterm exam, I plan on being 12 multiple choice questions and 4 short answer questions, and it should take about 90 minutes to complete and stuff like that. It should be good to go. And then the next time I see you, like probably the following lab period, I'll return the midterm to you with a summary sheet which says how you're doing in the class as of this time. So no big deal. The midterm will be closed note, no books or anything like that allowed. You will be allowed a periodic table, but I will provide it for you. Don't bring your own or anything like that. Should be pretty chill. Of course, if you have questions on this and you want to confirm, definitely let me know. I'm happy to help. And definitely I wish you the best of luck while studying for the midterm. Okay, with all that out of the way, let's start the review and let's get into some questions that hopefully will help you prepare for the midterm. This question is a question on balancing reactions, all right? And you can see up there's a reaction between H2S and SO2 to make sulfur by itself. That's elemental sulfur plus water. And it says, what statement regarding this reaction is true? And there are 5 possible answers there. In this question, you will definitely want to balance the chemical reaction to answer it. So do that part first, and then see if you can interpret that to get into the right answer. So this would be a good place to pause the recording, and when you're ready, unpause it, and we'll talk about the answer. So pause your recording now. Okay, I think, assuming at this point that you have tried the problem yourself, and let's check this out. So when you're doing this problem, all right, you can see you've got a lot of pieces up there to balance. Sulfur is by itself, all right? And sulfur would be the last thing I would want to balance, because you can see like sulfur is in both of the reactants, the H2S and the SO2. So for this one, when I look at this with my eye, I see, aha, SO2 has 2 oxygens, and oxygen is only in water. So I would start by putting a big 2 right there, because that will make the oxygens balance. So oxygen is down. Now I'm going to work on hydrogen, and you can see by putting the big 2 there to balance the oxygen, we now have 4 hydrogens. On the reactant side, hydrogens come in 2 in H2S, so let's put a 2 right there. And then, if all is said and done, I've got 2 sulfurs on H2S and 1 sulfur on SO2, so 3 sulfurs total. I believe that's going to be 3. Now, if you're ever uncertain as to how this all works out, I highly recommend that you balance the reaction. So let's balance this real fast. I'm going to put down the hydrogen, that's a H right there, sulfur and oxygen. And the left and right sides represent the reactant and product side. So on the reactant side, with my big 2 by H2S, I would have 2 times 2, 4 hydrogens, and 2 times 1, 2 sulfurs in the H2S. And in SO2, the other reactant, I have 1 more sulfur. Notice I had +1 right there. All right, just makes it easier for me. And SO2 has 2 oxygens. So on the right side, the product side, if we've done this right, everything will be balanced. So 3 sulfurs would be a 3 right there. 2 times 2 for water would be the number of hydrogens, or 4, and 2 times 1, 2 oxygens. And if you look, the numbers on the left, that's a pretty sloppy 4, sorry, the numbers on the left equal the numbers on the right, so this looks like it's balanced to me. So let's check or actually before we do that, let's assume that this is the balanced reaction. We can then go through and see which one of these statements are correct. So the first one says that 3 moles of sulfur are produced per mole of H2S. Well, I like the 3 part because we have a 3 right there. However, 3 moles per mole of H2S would not be correct. There's a 2 in front of the H2S, so it would be 3 moles of sulfur per 2 moles H2S. Answer A does not look right. Then it says 1 mole of SO2 is consumed per mole of H2S. Well, there's a 1 in front of the H2S. There's like an invisible 1 right there, and you shouldn't write that, but I'll write it here as for instruction. There's a 1:2 ratio of SO2 to H2S. It is not 1:1. Answer B doesn't look right. Then it says that a mole of water is produced per mole of H2S. Now initially that looks like, from the balanced reaction, like it would be 2 waters for every 2 H2S, all right? But if you reduce that down to common denominator, i.e. divide both of the 2's by 2, you're going to see that that one is right. 1 mole of water is produced per mole of H2S. So 2 moles of H2S could create 2 moles of water, and 3 moles of H2S would record 3 moles of water, etc., etc. But before we do that, let's look at the other ones here. D, the total number of moles of products is always equal to the total moles of reactants. That is not the case. All right, you can see from this reaction, which is balanced, that we don't have that. There's a 2 and a 1 on the reactant side, so that would be 3 moles of reactants. And on the product side, there's a 3 and a 2, 5 moles of products. So 3 moles of products obviously is not 5 moles of products. The moles of atoms will be the same, but the moles, the stoichiometries on the reactant side are not equal to the stoichiometries on the product side. So answer D is not right. Answer E is not right. If C is right, I think answer C is going to be right, and it is. All right. So when you balance this reaction out, 2H2S plus 1 invisible 1, SO2 makes 3S plus 2 waters, and the relationship between H2S and H2O is 2:2 or 1:1. Good to go. In this reaction, we're putting 2 moles of CCl4 with an excess of HF, and 1.7 moles of CCl2F2 is obtained. And here's the reaction. So we have an excess of HF, which means we don't have to worry per se about limiting reactants. You want to base your calculations on the CCl4 and the 2 moles of CCl4. And then it says that 1.7 moles of CCl2F2 are obtained. And then it says which statement here is true. And you can go through those and pick the one that's correct. The last one, infinite diversity and infinite combinations, is a really cheesy reference to the original Star Trek. Long story, but anyway, I'm really into Star Trek. I couldn't resist. I'll also let you know that's not the answer. Darn it! See if you can figure out which of the answers, A through D, is correct. This would be a good place to pause the video, work on it, and then when you're ready, unpause it. So pause your video now. Okay, at this point, I'm going to assume that you've done the problem and you want to talk about the answer, which is awesome. So this is showing the power of a chemical reaction and how chemists can use a chemical reaction to predict products and all kinds of interesting things. Now, let's go through these and see what's going on. First of all, unfortunately, answer E, my beloved Star Trek, is not the right answer here, so let's take that one out. All right, so first one, theoretical yield for CCl2F2, 1.7 moles. Now, to figure out what the theoretical yield is, all right, we really should start with reactants. And as we talked about, 2 moles of CCl4 is the important part. You can see that a lot of stuff is focusing around the CCl2F2. And honestly, in this problem, no one really cares about HCl, so just ignore that one, okay? Now, 2 moles of CCl4. Every 1 mole CCl4 creates 1 mole CCl2F2. So 2 times 1 over 1, the theoretical yield of CCl2F2 is certainly not 1.7, it's 2. All right, and you can write that out formally. 2 moles CCl4 times 1 mole CCl4 per 1 mole CCl2F2, you can see that this is going to come out to be 2 moles CCl2F2. And this number, all right, which I use the stoichiometric factor 1:1, that's the theoretical yield. The theoretical yield is 2 moles. It is not 1.7 moles. 1.7 moles is the actual yield of the product, all right? Actual yields kind of have to be given to you, and that's what the 1.7 moles of CCl2F2 is. It is not 1 mole, so B is also incorrect. C, percent yield for the reaction is 85%. Well, let's figure it out, all right? Theoretical yield, percent yield is equal to the actual yield divided by the theoretical yield times 100%. It's kind of sloppy, my apologies. So in this case, we saw that the 1.7 moles is the actual yield. 2 moles is the theoretical yield times 100%. And in my calculator here, I'm going to enter that in real fast. I get 0.85 times 100%. I'm getting a theoretical yield of 85%. So I believe answer C is correct. But let's look at D first and stuff. It says the theoretical yield cannot be determined unless the exact amount of HF used is known. That's incorrect. If it says that HF is an excess, that means we don't have to worry about it. CCl4 is like a limiting reactant, so it's really going to determine what all the different pieces are. So I'm pretty sure the answer here is going to be C, and it is. And you can see down here what I did is I first calculated the theoretical yield. This is a little bit fancier than my cheesy pen scratching up there. 2 moles times the ratio of 1/1 tells you the theoretical yield, and then percent yield, actual divided by theoretical, 1.7 divided by 2 times 100%, 85% yield. So if you've got this question down, you know how to find a theoretical yield, and you can figure out the percent yield if you're given the actual yield, of course. Cool. Burning sulfur in an atmosphere of fluorine produces the very stable compound SF6. SF6 is actually one of the worst, apparently, things for greenhouse gases, I guess. So SF6 is actually a controlled substance now, which is interesting, sulfur hexafluoride. Anyway, we wish to produce 2.50 moles of SF6. So what are we going to need here? How many moles of S8 and how many moles of F2 are we going to need? And from this information and that balanced equation, you can do it. You can use the stoichiometric factors to go from SF6 to F2 or whatever. See if you can do this on your own. Pause the video, and when you're ready, you can unpause it. So pause the video now. Okay, at this point, I'm going to assume that you've done the problem, and that's totally fine. So in this problem, we want a desired amount of product, SF6, and you want to calculate what the moles of the other pieces are. And to do this, we're going to use those stoichiometric factors like we used on the last time. So let me show you how you'd go from the SF6 to the F2. You would start with the 8 moles. Thanks for playing. So let me show you how to do this. You would start with the given amount, the product that you want, 2.50 moles SF6. And if you wanted to do fluorine, you would use 8 moles SF6 for every 24 moles of F2. And again, these aren't magical numbers here I'm using. They just come directly from the balanced equation, okay? So 2.50 times essentially 3 is going to be 7.50 moles of F2, all right? So I'm going to assume then that answer A is correct because that's the only one that's 7.50. Now, this number, 0.313, you should be able to get. You'd start with 2.50 moles of SF6. You'd still have 8 moles of SF6 on the bottom, but in the top you would have 1 mole of S8. So 2.50 times 1/8, I believe, is 0.313. And if you do this, it does come out to be answer A. So in this problem, you use those stoichiometric factors once again to find the desired amount. So in theory, if you put 0.313 moles of S8 with 7.50 moles of F2, you would end up with 2.50 moles of SF6. Kind of a powerful technique. If you have a balanced equation, there's a lot of things you can do, and this is like one example of how that works. Ammonia is prepared by the reaction nitrogen plus 3 hydrogen makes 2 ammonia. And in this problem, we have 10 moles of nitrogen, and mixing them with 25 moles of hydrogen, the amount of NH3 produced will be, and there's 5 different answers. So see if you can use your understanding of the stoichiometric factors to figure out what's going on. Also note that because there are 2 reactant amounts, you've got moles of N2 and moles of H2. I would definitely be on the lookout for a limiting reactant problem here. If you see 2 mole amounts, those are almost always a limiting reactant problem. It doesn't say anything in this problem about limiting reactant, but I bet it is. So anyway, see if you can do this. This would be a good time to pause the video, work on the problem, and when you have the answer, you can unpause it. So pause the video now. At this point, I'm going to assume that you have done the problem and you want to see how you did on it, which is fantastic. In this problem, you're going to do the process we've used earlier. You're going to take the reactant amounts and figure out how many moles of product will be created. So as an example of that, you could start with 10 moles of N2, and there's 1 mole of N2 for every 2 moles NH3. So from the nitrogen, it looks like you'd have 10 times 2 over 1, 20 moles of NH3. But you really should do it for the other one too, all right? Because just because 25 looks like it's big compared to 10, but the stoichiometry sometimes will be really, really weird. So also do this from the other reactant's perspective. So you can start with 25 moles of H2, and there are 3 moles of H2 for every 2 moles NH3, and again the 2 and the 3 just come from the balanced equation. I'm going to take 25, multiply it by 2 over 3, and sure enough, I get 16.7 moles NH3. So we've got a problem here where the nitrogen says we can make 20 moles of NH3, but the hydrogen claims we can only make 16.7. And if your boss says, hey, how much ammonia NH3 can we make here? Well, you'd better give him the right amount. And the answer will be the smaller number. So what this says is that the amount of NH3 that's made, not 20, all right? The hydrogen, the H2, can only produce 16.7 moles of NH3. And this is an example of a limiting reactant problem. If you see two reactant amounts, all right, like here it was N2 and H2, you really should test both of them to see how much product can be made. And that's what we did right here. If you quoted your boss a 20 mole NH3 yield, you probably should be fired because you didn't check the other reactant. Bad call. In this problem, we would call the hydrogen H2 the limiting reactant. It's limiting how much product, NH3, that can be made. And because it's the limiting reactant, that means that 16.7 moles is the theoretical yield of NH3. That's how much we should be able to make. And then finally, by default, because nitrogen is not the limiting reactant, it's going to be one of the excess reactants. There will be nitrogen left over at the end of this reaction. So if you can do this kind of problem, you totally have this process down. What mass of sodium carbonate with a molar mass 106.0 grams per mole is required for complete reaction with 25 milliliters of 0.155 molar HNO3? So in this reaction, sodium carbonate is reacting with nitric acid, and this is a double displacement exchange reaction. So the sodium and the hydrogen are trading places. You end up with sodium nitrate, and you end up with what looks like H2CO3, which we talked earlier breaks down to CO2 and water. And in this question, we basically want to neutralize the 25 milliliters of 0.155 molar HNO3. We want to add enough sodium carbonate to make that happen. So using the balanced equation and your knowledge of how moles to mole ratios work, see if you can figure out which of those answers is the right answer. This would be a good place to pause your video and work on it. And when you're ready, you can unpause it. Pause your video now. Okay, at this point, I'm going to assume you've tried the problem. You want to see how you did. So very cool. Remember that big M, the 0.155 big M, that means moles per liter. And so if you wanted to find moles of HNO3, you could take 0.155 moles per liter and multiply it by 25 milliliters as liters. So remember, there's 1,000 milliliters per liter. So 0.155 times 0.02500 liters would be the way to find the moles of HNO3. You do have to use liters in this one. Big M is moles per liter, so turn 25 milliliters into liters first. Now, once you have moles HNO3, the balanced equation down here says 2 moles HNO3 per 1 mole Na2CO3. So the moles of HNO3, you basically want to divide by 2 to get the moles of Na2CO3, or you could multiply by 1/2. That would be fine. That'll allow you to find the moles of sodium carbonate needed to react with the HNO3. And from that number, moles of Na2CO3, you can use the molar mass, multiply, to get the grams of sodium carbonate. So if you've done all this, then here's the process itself. I turned the milliliters into liters, multiplied by the molarity of the HNO3. Here's the 1:2 ratio we talked about, and again, that came straight from the balanced equation right there, no magic. And then we multiplied by the molar mass of the compound and of the Na2CO3, and of course that came out to be answer C. So if we put 0.205 grams of sodium carbonate in with that much nitric acid, we should have neutralized all of it. You'll end up with CO2, water, and sodium nitrate. Good to go. A piece of copper, 5 grams of copper specifically, is heated for 2 seconds and 100 joules of heat energy is transferred to the copper. The temperature of the copper goes from 20 degrees to 71.9 degrees Celsius. We can use this information to calculate the specific heat capacity of the copper. So this problem is going to be one where you're going to use Q equals mc delta T. And the goal is to find the C of that equation. C is the specific heat capacity. Specific heat capacity is always a positive number. Answer E would not work here. I'm going to let you know that right now. I'm putting it in there just to talk about it. Negative heat capacities don't fly in thermochemistry. So the number will be A through D. Again, Q equals mc delta T. Solve for C. See if you can figure out which one it is. So this would be a good place to pause the video, work on it, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming that you have tried the problem and you want to see how you did on it, which is fantastic. So let's talk about it. This problem, Q equals mc delta T. And it's the C part that you want to solve for here. The Q is the heat, the joules, all right? So for Q, you'd put 100 joules in there. And the M term is literally mass in grams, so you would put 5.00. Now, delta T, final minus initial temperature. Initially, the copper was 20, and at the end, it was 71.9. So your delta T here would be 71.9 minus 20, or 51.9. So C will be Q divided by M and delta T. You would go 100 divided by 5 divided by 51.9. And if you did this, it comes out to be answer B. Right here, you can see the steps. C equals Q divided by M delta T. 100 joules for Q, 5 grams for mass. Here's the delta T, final minus negative. Good to go. Delta T can be in Celsius or Kelvin. Notice the units of heat capacity are in Kelvin, but I use Celsius. A delta T, change in temperature in Celsius, is going to be the same as a delta T in Kelvin. So you can use either one. And in this problem, since I gave you Celsius temperatures, it makes sense to find it in Celsius. But again, there's nothing wrong with converting to Kelvin and then doing delta temperature in Kelvin, but I promise you're going to get the same 51.9 number. When 108 grams of water at 22.5 degrees Celsius are mixed with 65.1 grams of water at an unknown temperature, the final temperature of the mixture, 47.9 Celsius. What was the initial temperature of the other sample of water? Okay, so in this problem, we have a cold system, 22.5, and we have water at an unknown temperature. But the reason I said it was cold, the final temperature, 47.9 degrees. So notice that the cold 22.5 went up to 47.9. On these kind of problems, remember it's all about hot plus cold, making something that's in between, or warm, I guess would be the best way. So 22.5 is the cold, and we know that because the ending temperature was warmer, all right, 47.9. That also means that the other water system had to be at a temperature greater than 47.9. It was hot. Hot goes down to warm. Cold goes up to warm. We've got the cold going up to warm. We just need to know what the hot is. So the goal here is to find the initial temperature of the other sample of water. Now, in thermodynamics, the hot plus the cold, and that's supposed to be as Q hot plus Q cold, equals 0. And that's a way that scientists say that no energy has been created or destroyed. Now, each the hot Q cold and the Q hot, they're both going to be an mc delta T, all right? C is the heat capacity of water, and I hope you know that number or can look it up quickly. I'm not going to tell you until I answer it. Fascist chemist. Anyway, the cold has a mass of 108 grams. The hot has a mass of 65.1 grams. And delta T for the hot is going to be final, 47.9, minus the initial hot temperature, Ti. And that's what you want to solve for. Of the delta T here, you'll have TF minus Ti. You want to solve for Ti. You've already got TF, but you don't have Ti. So see if you can use this information to find the answer. Some of the answers do not make sense based on the thing we just talked about. So see what you can do. This would be a good place to pause the video, and when you're ready, unpause it, and we'll talk about the answer, see how you did. Pause the video now. Okay, at this point, I'm assuming you've tried the problem and you want to check out your answer, which is fantastic. So Q cold plus Q hot equals 0. That's thermodynamics saying no heat can be created or destroyed. We know that we've got something cold, the 22.5 degree sample, and we've got something hot, and they're coming together to make something warm, 47.9. So our answer, final answer for the hot thing, the initial temperature of the hot, it's going to be larger than 47.9. 8.9 does not make any sense here because that would be colder even than 22.5 Celsius. That doesn't make any sense. Also, it doesn't say anything about boiling water or boiling gaseous steam, and water boils at 100 Celsius. So 274 Celsius also doesn't make any sense. At 274 Celsius, we would expect our water to be a gas, not a liquid. And so that also would not, we'd have to have a phase change. We'd have to have mass times the heat of vaporization to figure out how that all works out. So the answer is going to be B, C, or D. And what you want to do is have MC delta T for hot plus MC delta T for cold equals 0. And there's different ways to write that. It's no big deal. Now, the heat capacity for liquid water is a number I want you to know. And that number, which is C here, 4.184. So the 4.184 will be the heat capacity for both hot and cold. All right. So on this problem, what I did is instead of writing Q hot plus Q cold equals 0, I put Q cold on the other side, Q hot equals negative Q cold. And each of those is its own MC delta T, all right? So you can see here for the hot side, here's the mass of the hot water, heat capacity, delta T, final minus initial. And it's that Ti that we want to solve for, by the way. And that equals negative Q cold, negative mass of the cold, heat capacity of the cold, and delta T 47.9 minus 22.5. Now, 4.184 actually cancels in this one. So if you didn't know 4.184, oh, you're lucky. No, seriously, we're going to use 4.184 a lot, so make sure you know it, but really you don't have to use it here, okay? And you basically just want to solve for Ti. Now, the whole right-hand side is just going to be a number, all right? And the left-hand side, you can reduce down quite a bit, all right? Like 65.1 times 47.9 is some number. And then that also times Ti is what you want to do here. So when you go through the math, and I encourage you to follow it, looks like the initial temperature, 90 degrees Celsius, all right? So the water started at 90 degrees Celsius. It was mixed with water at 22.5 Celsius, and at the end, it ended up at 47.9 degrees Celsius. Kind of a cool way to figure these things out. Propane, which is used in a lot of barbecues and stuff, propane has a standard molar enthalpy of combustion, negative 2044 kilojoules. So what that means is that if you burn, which is what that reaction is, it's a combustion reaction, if you burn 1 mole of propane, you're going to get negative 2044 kilojoules out. And this question says, what's the standard enthalpy change for the combustion of 3 moles of propane? So instead of 1 mole of propane, you want to burn 3 moles of propane. See if you can figure out which of those answers is correct. This would be a good place to pause the video. When you're ready, you can unpause it. We'll talk about it. Pause the video now. Okay, I'm going to assume that you've tried the problem and you want to talk about it, which is totally cool. This is a combustion reaction. Something organic plus O2 makes CO2 and water. And for every mole of C3H8 that's burned, negative 2044 kilojoules come out. Notice here what you could do. You could write negative 2044 kilojoules per 1 mole C3H8. This is a way that I kind of prefer. It says that you get this much energy out for burning 1 mole of C3H8. And in the problem here, we have 3 moles of propane. So I'm going to write 3.000 moles C3H8. So in this problem, you basically want to take the negative 2044 and multiply it by 3. Then the moles of the propane will cancel out. You'll have just kilojoules left over. The answer comes out to be A, negative 6,132 kilojoules. This reaction was exothermic to begin with. The enthalpy was negative, so the answer had better be negative as well. That's important. You wouldn't want to use the positive version. So the negative 2044 times 3 would give you the answer. Lots of energy released upon burning propane. This is a reaction where we're taking silane, SiH4, reacting it with oxygen to make silicon dioxide and 2 waters. And it gives you some delta HF, some heats of formation values there. What I'd like you to do here is calculate the enthalpy for this reaction using those values. And for this kind of process, the enthalpy of the products minus the enthalpy of the reactants is what you want to do. And you can use these numbers here. Now, there are 4 reactants and products. I didn't give you the delta HF for one of them. See if you can remember why I didn't give delta HF for one of them. Anyway, this is a good place to pause the video, work on the problem, and when you're ready, you can unpause it. We'll talk about the answer. Pause your video now. Okay, at this point, I'm assuming you've tried the video and you want to see how you did, so let's get into it. On a problem like this, you want to have the sum, it's the delta H of the reaction. It equals the sum, that weird sigma thing, the delta H of the products minus the sum delta H of the reactants. And again, I can't draw on this thing, so it's so sloppy. I'm really sorry. But anyway, I hope you get the idea. Delta H of products minus delta H of reactants. All of these delta H of formations are enthalpies per mole. So the SiO2 we're going to use as is. We're just going to use that one. But because there's a 2 by the water, we're going to take this number and multiply it by 2. And that's going to be this part. That's the delta H of the products. Now you want to subtract, and remember always to subtract, the delta H of reactants. We're given the delta H for silane, so that goes over there. But notice there is no delta HF for oxygen. And the reason I didn't include it here was to make a point again that the heats of formation, the delta HF values, will always be 0 for the elements in their standard states. So any of the elements in their standard states are just going to be 0. So on this one, you don't have to worry about the O2s. They're just equal to 0. So to figure this out, you take products minus reactants. You take the SiO2, negative 910.9, plus 2 times negative 241.8, and those terms would be the delta H products. Then you subtract the only delta H of reactants that's needed, so minus 34.3. If you put that in your calculator, if you put that in your calculator, it comes out to be negative 1,428.8 kilojoules per mole. And again, you can see here, here's the delta H of products minus the delta H of reactants. The O2 was 0, so we don't have to worry about that. Make sure you do subtract the reactants. Once in a while, I'll forget that, which isn't a good thing. This is an exothermic reaction. These delta HF values are the ones from the table in problem set 5, and on an exam or something like that, I would give you the ones you need. I may not give you like oxygen. All right, you have to be hip about that. Sorry, fascist chemist instructor, but all stuff you can do. And honestly, if you don't have a value, it probably means it is 0 because your instructor is anyway. Which of the following equations below defines the standard molar enthalpy of formation for gaseous methanol, CH3OH? So this question is basically saying which one of these equations is a delta HF, all right? In the last problem, we used delta HFs to products minus reactants. And one of these three, not E, please care, all right? This hopefully is important somehow to your future and stuff like that. Methanol, if you do drink methanol, it does make you go blind. In the days of Prohibition, when people made illegal moonshine, a lot of times they would have their alcohol that they made in bathtubs or whatever, it would be contaminated with methanol. And if you drink the methanol with the ethanol, it'll make you go blind and stuff. So anyway, stupid answer. It's going to be A, B, D, C, or D. Anyway, see if you can figure out which of those it is. There's some specific rules for delta HF equations, and that's what I'm having you focus on this problem. So this would be a good place to pause it, think about it, see which one of those is the best answer, and when you're ready, you can unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm going to assume that you gave the problem a shot and you want to see how your answer did, so let's get into it. If you are creating a delta HF equation, which is what this is, and delta HF is the standard molar enthalpy of formation, all right, then a couple of things. You can only have 1 mole of product, all right? And if you look at A, B, C, and D, all of these have just 1 mole. If you had, for example, like a 2 right there, then you wouldn't want to use that, all right? It has to be 1 mole of product. But the other thing that's important here is all reactants must be elements in their standard states. So if you look at answer A, oxygen, O2, that's an element. That's its standard state. Oxygen is normally a gas. It's what you're breathing right now while watching this. It's not oxygen as a liquid. It's not ozone, something like that. That's oxygen's natural state. But CH4 is a compound, all right? It's a mixture of carbon and hydrogen. And in a delta HF, you can only have elements in their standard states. So A is not going to work because CH4 is a compound. And if you go down like C has CO, that's a compound, that's not going to fly. Water is a compound, that's not going to fly. So answer B here is the best answer. In this compound, in this equation, we have 1 mole of product, and the reactants are elements in their standard states. So carbon, hydrogen, oxygen are standard. H2 and O2 because they're diatomic. The carbon would be graphite, although it doesn't state that, but that's the cheap version, basically carbon, more common. So answer B here is the heat of formation equation for methanol. And again, important parts, 1 mole of product, and all reactants are elements in their standard states. In this equation, I'd like you to calculate the standard molar enthalpy of formation for FeCl2 using the following. And we have here 2 equations, both involving FeCl3. Now, be careful here. We're looking for FeCl2, not FeCl3. This is an example of Hess's law, and I want you to figure out essentially the heat of formation for FeCl2 using Hess's law and these 2 equations. This is going to be a good place to pause your video. You can work on this, think about it a little bit, and when you're ready, you can unpause it. We'll talk about the answer, so pause your video now. Okay, at this point, I'm assuming that you've tried the problem and you want to check out how you did. So let's, without further ado, let's get into it. Let's write out what the standard molar enthalpy of formation for FeCl2 would look like. And this is kind of like what we did in the last problem. But remember that standard molar enthalpy of formations, 1 mole of product, so FeCl2, and all reactants elements in their standard states, well, that's going to be Fe and Cl2. Those are the standard states for iron and chlorine. So this is the desired equation, and we want to make these 2 equations look like the last one, all right? And you can see that right now that's a little confusing. What I look for on these kind of problems is, for example, like we want iron as a reactant, and iron is a reactant right here. So probably then we can use this equation as is. But you don't want FeCl3 as a product, you want FeCl2. And the top equation, or the first equation right there, it has FeCl2, but it's a reactant. We want to have FeCl2 as a product. So I know right away then on that equation, we're going to have to flip it around. We're going to make the 1/2 Cl2 and FeCl2 as products, and FeCl3 will become a reactant. And when you do this, the delta H value becomes positive. You change the sign of it. It becomes positive 57.7 kilojoules. When you flip an equation, you change the sign around. So on this equation, on this problem, that's what I would do. And if you do that, you can see that's exactly what happens. I want iron as a reactant, so I'm going to leave that equation alone. But the other equation, I want to flip because I want FeCl2 as a product, not a reactant. And in the meantime, when you flip it, you can see what happens. The FeCl3 that's a product here will cancel the FeCl3 that's a reactant there when you add these equations together. And also you have 3/2 Cl2 and 1/2 Cl2. Subtracting 1/2 Cl2 from both sides makes that one go away, and you have just 1 Cl2. So the Fe plus Cl2 goes to FeCl2. And remember to change the sign of the delta H, but then negative 399.5 plus 57.7, delta H negative 341.8 kilojoules per mole, answer B. So this is an example of Hess's law, how it can be really handy for things. Pretty cool. Given the bond dissociation enthalpies below, calculate the standard molar enthalpy of formation for NF3. And it shows the reaction there. This is a heat of formation, which means 1 mole of product only, and reactants are elements in their standard states. So because these are both diatomics, we have to use the fractions, 1/2 and 3/2. Even I have to use fractions. I hate fractions, but anyway, that's my own problem. Anyway, in this kind of problem, what we're going to do is a problem we talked about in lecture where you take the bonds that are broken and you subtract the bonds that are formed. So what I would do to solve this problem is I would first draw the Lewis structures for N2, F2, and NF3. And from there, bonds broken means the reactants. You're going to break the reactant bonds. And from that, you subtract the bonds that are formed, which are the products. All right. This is the one time in this first midterm you will need a calculator, because in order to calculate bonds broken minus bonds formed, you're going to need the numbers. So at this point, I definitely recommend that you pause the video, work on the problem, see if you can get one of those answers using the table right there. When you're ready, unpause the video and we'll talk about the answer. Pause the video now. At this point, I'm assuming you've worked on the problem and you want to check it out, which is totally fine. So let's get into the problem and see what's happening. So the first thing you've got to do is you've got to draw the Lewis structures to figure out what you've got. Nitrogen, N2, is going to have a triple bond between it. We talked about that earlier in an earlier problem. So that's going to be the NN triple bond. F2, when you draw out its Lewis structure, has a single bond. So F2, you're going to break a fluorine-fluorine single bond. And then NF3, nitrogen trifluoride, the nitrogen is in the middle of 3 fluorines. The fluorines have a filled octet around them, and the nitrogen has a lone pair. Now that we have the Lewis structures, we can figure out which of those numbers we're going to use. And remember, it's bonds broken minus bonds formed. So we're going to break an NN triple bond and an FF single bond. So 946 plus 159 would be that part. And then it's bonds broken minus bonds formed. And the bonds formed are the products. Now NF3 has 3 NF single bonds. So that means we're going to take that 272 and multiply it by 3. And that's what we subtract from the other two values. So when you do all of this, and I'm going to let you do this in your calculator, in a normal face-to-face class, this would be an iClicker exam review. And so what I would do is present a question like this one right here. I would give the students a few moments to kind of think about what the answer should be. They could enter their answer into the iClicker system, and then we talk about the actual answer once most people had responded. And they get extra credit and stuff like that way. Well, in this version of the exam review where it's on a video, I don't have a mechanism to grant extra credit opportunities, so I'm very sorry. But what I will do is I'll announce the question. I'll give you a few minutes to work on it. There'll be a place where I'll say pause the video, and I encourage you to pause it, work on the question, and when you're ready, you can unpause the video and we'll talk about the actual answer. You can see how you did. And again, this is for your information only. All right. I don't mind if you get all the questions wrong. I bet then that you have a lot you're learning a lot while you're going through the questions, and that's kind of the goal of these problems. So anyway, this is the first of these questions. A sample of gas has a volume of 222 milliliters at 695 millimeters of mercury and 0 degrees Celsius. And the question is, what should be the volume at the same sample of gas if it were measured at 333 millimeters of mercury and 0 degrees Celsius? So see if you can work on this question. Pause the video and you can work on it. And when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've had enough time to work on the problem and you want to see how you did. So without further ado, let's get into it. This is an example of when you have more than one quantity changing in a gas, and there's different ways to approach it. One way would be to try to see specifically like which ones are changing. And if you look at this problem, the pressure is 695 millimeters of mercury initially, and it ends up being 333 millimeters of mercury, so it's certainly changing. The temperature is listed, but the temperature is the same. So really, temperature doesn't play a part here. It's not as important. On the other hand, you start with this volume, and the question is, what is the new volume? So there's a couple ways you could do this, and one way would be to use P1 V1 equals P2 V2. And if only pressure and volume change, which is all that's happening right here, you can leave the units as they are. You just want to make sure the pressures are the same kind of units and the volumes are the same kind of units. So you don't have to use atmospheres for pressure and liters for volume if it's just P1 V1 equals P2 V2. Remember that if you have a temperature change, you must use Kelvin. You don't want to divide or multiply by 0. That would make things really messy. Another way to do this problem, and what I kind of use more and more, is I go back to the ideal gas law. P and V are changing, but everything else, nRT, is the same. So what that means is if I have a P1 V1 set of conditions, that's going to equal P2 V2, because again, N, R, and T are not changing. Those are all a constant. So by hook or by crook, find out that P1 and V1 equals P2 V2. It doesn't matter how you do it. We want to solve for V2. And so V2 equals P1 V1 divided by P2. And again, you can literally put those numbers in just as they are. And if you do that, you should get 463 milliliters, the new volume. Again, you don't really have to use the temperatures down there. I included P1 V1 over T1 equals P2 V2 over T2. And I did that because I wanted to remind everyone you must use Kelvin, don't use Celsius. All right, that's like a big time bad boy. And again, you don't have to convert to liters and atmospheres either. You can just leave them as milliliters and millimeters of mercury. Pressure and volume, if you will, are a bit more flexible. Finally, the final answer, negative 155 milliliters, doesn't make any sense. Volume should always be a positive number. It's three-dimensional space. Negative volume is fun for science fiction people like me, but not really very helpful in a science world. gas density. Which has the greatest density at 25 degrees Celsius and 1 atmosphere of pressure? We're going to assume that these are all gases, and I'd like you to try and figure out which one has the greatest density at those set of conditions. This is a good place to pause the video. You can work on the problem, and when you're ready, you can unpause the video. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've tried the problem and you want to check out your answer, see how you did, so let's get into it. If you remember one of the other ideal gas laws, not the PV equals nRT, but the other one which is kind of helpful, PM equals dRT. I called this the evening dirt equation, which is totally silly, but it maybe helps you remember. The important thing for us here is that this equation does show how the density of a gas, the D part right there, relates to the M, which is the molar mass of the gas. So in a sense, when it comes to gases, the heaviest molar mass, the biggest molar mass, will have the biggest density. So what you want to do on that list is go through and find out the molar masses of each one of those gases. So for example, oxygen, O2, has 2 oxygens, so 2 times 16 on the periodic table, about 32 grams per mole. Nitrogen, the next one, has 28 grams per mole, 2 times 14. So we would say that O2 has a bigger density than N2 because it has a bigger molar mass. You can go through that list. H2 is smaller than O2, 2 grams per mole. CO2 is bigger than O2. It's about 44 grams per mole. So CO2 would be more dense than oxygen at those conditions. However, the biggest molar mass of all belongs to xenon. Xenon on the periodic table, which is a noble gas, 131 grams per mole. So bigger molar mass, bigger density. We would say that xenon has the biggest gas density at those conditions in this list. Diborane, which is B2H6, reacts with oxygen to give boric oxide, B2O3, and some water. If 1.5 liters of diborane, is mixed with oxygen, what volume of oxygen is required for the reaction? And assume constant temperature and pressure. See if you can solve this problem on your own by pausing the video, working on it, and when you're ready, you can unpause the video. Pause the video now. Okay, I'm assuming you've worked on the problem and you want to discuss the answer, so without further ado, let's do it. Instead of liters of diborane, let's assume that this question said if 1.5 moles of diborane is mixed with oxygen, how many moles of O2 would you need? Well, in the old days, we would have seen that there's a 1 mole B2H6 to 3 moles O2 ratio. So if we had 1.5 moles, we would multiply 1.5 moles by a 3/1 ratio. That converts moles of diborane to moles of oxygen, and 1.5 times 3 would be 4.5 moles. All right, that's if this question was moles. But obviously this question is liters. All right, one method you could use to solve this particular problem is you could take the liters, you could assume, say it was STP, standard temperature and pressure, and you could use that to find moles of diborane. You'd multiply by 3 to get moles of oxygen, and you'd use the same recommendation that you used earlier to find the volume of O2. And that would be a lot of work, but you could do it. But another way you can do this problem is to go back to ideal gas law. PV equals nRT, all right? And I want you to focus on the V and the N, all right? It says that the pressure and the temperature are constant, and R is, of course, a constant. So notice that volume and moles are on opposite sides. That means they are proportional to each other. So as one goes up, the other one goes up. If one goes down, the other one goes down, all right? Moles, if moles goes up, then volume goes up, and if moles goes down, volume goes down. It doesn't make as much sense for volume to go down and moles to go down because that's quantity of mass. But anyway, I digress. In this problem, the liters are the same as moles in how they work in this kind of problem mathematically. So if 1.5 moles of diborane needed 4.5 moles of oxygen, 1.5 liters times 3 over 1 will give you the equivalent answer in terms of liters of O2 for this stoichiometry. So 4.5 liters of oxygen is correct. And we can do the 3-to-1 stoichiometry because moles and volume are also proportional to each other. So just like we use 3-to-1 mole ratio, here we're going to use 3-to-1 volume ratio. So it should take 4.5 liters of oxygen to react with 1.5 liters of diborane. You can do this kind of problem as well with pressure if you assume that temperature and volume are constant. So that's kind of a powerful technique sometimes to use. This is a lot easier than trying to go through the ideal gas law, etc., etc. Diborane, again burning in air, same equation as before. There are 3 gases in this reaction. So diborane, B2H6, oxygen, and water. I'd like you to place these gases in order of increasing velocity, i.e. from slowest gas to fastest gas. See if you can figure this answer out. If you need to, pause the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming that you've worked on the problem and you want to talk about it, so let's do so. When it comes to the speed of gases, as long as they're all at the same temperature, and for a reaction like this, that would be a very fair statement to make, then what it means is that the smallest molar mass will be the fastest, and the biggest molar mass will be the slowest, all right? So for this problem, what you want to do is put the B2H6, 3O2, and water in terms of molar mass, all right? So water is about 18 grams per mole when you figure out its molar mass. O2 is about 32 grams per mole. So because water has a smaller molar mass, it should be fastest, and oxygen with the bigger molar mass would be smaller. B2H6 has 2 borons, which are about 11 grams per mole each. That's 22, plus another 6 or so for the hydrogen. B2H6 is going to be about 28 grams per mole, and that falls in the middle of water and oxygen. So if we want these in order of increasing velocity, we want the biggest one first, and I believe that's going to be O2. And then B2H6 is a molar mass in the middle, so that would be the middle speed. And water, with the smaller molar mass, water should have the fastest speed. So it goes O2, B2H6, H2O. And there's the molar masses. So you can see it went from heaviest molar mass to smallest molar mass. Chemists can use molar mass in lots of different ways, and this is just one example to see which one are going to have the fastest speed. Equal masses of helium and neon are placed in separate containers of equal volume at the same temperature. Compare the pressure of the gases, all right? And you might be tempted to automatically put D, too much pressure, science, but trust me, that's not the right answer here. So anyway, equal masses of helium and neon. See if you can figure out which one of those is the correct answer. I recommend pausing the video. You can work on it, and when you're ready to talk about the answer, unpause it. We'll talk about the answer. Pause the video now. I'm going to assume you've worked on the problem and you're ready to talk about the answer. So without further ado, let's get into it. The key to figuring this question out is to understand what pressure is. And pressure is about collisions with walls of the container, or pressure is about collisions with molecules with each other. Pressure is proportional to moles. And I know that because PV equals nRT. So P and V are on opposite sides. As the moles goes up, the pressure goes up. So what we want to do here is, because we have equal masses, is just pick some mass, all right? And I would like to pick 4 grams. Now you can pick 1,000 grams, 10 to the minus 7th grams, whatever number you want. But for me here, it's going to be easiest to think about 4. I'm doing that because I want to figure out how many moles of helium and neon we would have if we had 4 grams of each gas. Now 4 grams divided by 4 grams per mole, which is the molar mass of helium, that means 1 mole of helium. Now neon, on the other hand, is about 20 grams per mole if you look it up on the periodic table. So 4 grams, same mass as helium, divided by 20 grams per mole. This is going to be about 4/20ths, 2/10ths, all right, 1/5. This would be about 0.20 moles of neon. So notice that the moles of neon are less than the moles of helium. And you can pick any number you want. You don't have to pick 4, but you're always going to get this. The moles of neon are less than the moles of helium. And that's because the molar mass of the two substances is different. Well, fewer moles means less pressure. So we would expect, because there are more moles of helium, we would have a greater pressure of helium. We would expect the pressure of helium to be greater than the pressure of neon because there's more moles. So there's formally what I tried to do in the upper right hand corner. You end up with less moles of neon, which is less molecules running around colliding with each other. You have more molecules, or atoms I should say, of helium running around, so they collide with each other, more pressure. Pretty interesting use there. But you can see how if it says equal masses, just pick some number, any number, whatever's easier, and then figure out the moles, and from moles you can figure out pressures, stuff like that. Okay, that's the end of the video introduction to the first midterm exam. I hope this has been helpful. There's lots more resources for you to get more practice on these problems. So there's practice problem sets in both the companion and online. You can also look at things like concept guides and chapter guides. And the end of our textbook, basically every other question, the answer is given in the back. So you can kind of test yourself to see how you're doing. All right, good luck with your studying. I wish you the best on the midterm and have a great day.